So just a little reminder for this one is if we look over at our Pascal's triangle, don't forget that if I can represent them by numbers, 1, 1, 1, 1, 2, 1, etc., or I can start representing them using the notation. For example, this row, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And remember that to get, for example, the one below, we're taking the 2 that surround it. So 3 choose 1 plus 3 choose 2 gives us 4 choose 2. So the top number goes up 1. The bottom number will be the biggest out of the 2 you're adding together. So another way of saying that, remember, is, well, there's so many ways to say it. K choose R plus K choose R plus 1 will get us to the next row, so the K plus 1th row. So K plus 1 choose, and we'll take the bigger, whichever's the bigger one, the R plus 1. All right, so just a reminder of that because we're going to use that one here. So just make sure you've kind of gone through that and you remember that. Okay, so a little bit tricky because you've got to really pay attention to detail for this one. So again, I'm going to be naughty and skip. Let P of n represent the proposition. Have a look at P of 1. Is it true? Well, if I look at the left-hand side, I'm saying x plus a to the power of 1, which is x plus a. If I look at the right-hand side, I'm going from r equals 0 to n equals 1, so that's going to be 2 terms. So if I look at the 0 term, I've got 1, choose, 0, choose, and my r is 0. Let me just write it out properly. So we're going from r equals 0 to 1 of 1, choose whatever r is, x to the 1 minus r, a to the r. If we have a look at that, so if I make, first of all, r 0, I've got 1, choose 0, x to the 1 times a to the 0 plus 1, choose 1, x to the 1 minus 1, so 0, and a to the 1. Alright, so what do we have there? Hopefully x plus a. Let's have a look. So 1, choose 0, we've got both of these equaling 1s. So we've got x times a to the 0 is 1. So that first term is x. Second term, we've got 1 times x to the 0 is 1. So we're going to get a. So both our right-hand side and left-hand side are equaling x plus a. So we're all good there. All right. So that was just checking our proposition with 1 in it. I'll write our P of k down because we're going to use it as our assumption. So if P of k is true for some arbitrary integral k is greater or equal to 1, then we've got x plus a to the power of k being the sum from 0 to k. This is a problem because of my handwriting and these letters all look the same, my k's and my r's. So we're summing from 0 to k of k, choose x to the k minus r and a to the r. Alright, and what are we required to prove? I'll just put it over here. So our proposition of k plus 1 will give us x plus a to the power of k plus 1 being equal to the sum. This time we want to sum from 0 up to k plus 1, so really pay attention to these small details. And we've got k plus 1, choose r, x to the k minus r plus 1, k plus 1, but minus r, so same as k minus r plus 1, and a to the r. Okay, so if we look at the left-hand side of that, which is x plus a to the power of k plus 1. So I know I want to use x plus a to the k, so I'm just going to split that up, x plus a times x plus a to the k. Because I can use x plus a to the k, I can use the assumption and put the sum from r equals 0 to k of k, choose r, x to the k minus r, a to the r. All right, and what we're going to do with that is we're going to times it by x, and then we're going to times it all by a. So we're just expanding out the brackets. All right, and I should have written from P of k because that's what I've used. All right, so if I times everything through by x to start with, then I've got this sum which is going from r equals 0 up to k. And it's still going to be k choose r, k choose r, hasn't changed that. But I'm timesing everything by x. So this was x to the k minus r. It now becomes x to the k minus r plus 1. K minus r plus 1. So if you need to, write out a few terms, and you know, the first 3 terms and the last term or something like that. And you can see as you times x through all those terms, all you're changing is that x value. All right, plus now I'm going to times everything through by a. So again, if you can't see it, write out a few terms. All right, so I'm still going to have k choose r. My x is not changing, so that's to the power of k minus r. It's my a that's changing, timesing everything by another a, so it's going to be to the power of r plus 1. Now, if you have a look, we're going to actually just change one thing at a time so you can see it. So keep this first term the same for a second. So that is a k minus r plus a 1, a to the r. But this one, so if I have a look at what I'm heading towards, I only want a to the r. That's what I want. So how can I change this expression to just have an a to the r but still give me what I want? All right, so I want it still to be, let me do it in green, I want that to be a to the r instead of r plus 1. And if you think about it, so at the moment, if I had expand this out, maybe this second term out a little bit, it starts at r equals 0, so I've got k choose 0, x to the k minus 0, a to the 1. And the next one would be r equals 1, x to the k minus 1, r equals 1, so that's a squared, etc. All right, and that's what I still want, but I want it with an a to the r. So if you think about it, that r, if I start that r, I want 1, 2, etc. all the way, actually up to, if I go dot, 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 the last one will be when I sub a k in for r, so I'm going to get a to the k plus 1 there. I could also actually just, so k choose k plus 1, k choose k, x to the, I'm putting k in, so that's going to be 0. So that's what I want. Now, how can I get that differently? Well, I could start it, instead of r equals 0, I could start at r equals 1. That would give me a to the 1, a squared, and I could go all the way up to k plus 1. That would give me this a to the k plus 1, but it would also change the other parts in that term. So let's have a look at how we can fix that. So instead of having k choose r, which is what we've got here, we still want these k's, so we still want k. Oops. But what can we start with instead? So I don't want k choose 1, which is what I'll have if I keep it as r. I want k choose 0. So let's do our r minus 1. Just take it back 1. And then I'm going all the way, if you think from 1, I'm going really c0 up to k plus 1 minus 1, which is k. So up to ck, which is what I want here. So let's look at our x term. What power do I want? I want to start at k, and so if I put I'm not going to fit this. So if I kept it at k minus r, and I started with r equals 1, I would have k minus 1. But that's my next term. So the first term I want is the k. So how about I just add 1 to that power, and now it's going to give me exactly the same stuff. It's just I've changed, so I do have the a to the r, and so I've just got different limits, but it's the same. Same. It looks the same. All right, so once I've done that, it looks a little nicer because it matches this, what I'm looking for, the a to the r. It's got the x to the k minus r plus 1. It doesn't have k plus 1 choose r, but it does have k choose r minus 1. So this is the only bit that's not quite looking right. But again, if I have a look at here also, it goes from 0 to k plus 1, and my green one is going from 1 to k plus 1. That's okay, maybe some of my other terms are in this blue bit here. All right, so let's have a look now. So what I want you to remember from the very beginning is that, and we can say it this way, k choose r plus k choose, let's go r minus 1 plus k choose r is going to give me k plus 1 choose the bigger one, so r. All right, so noting that, what I'm going to do is take out, and I'm going to run out of room totally. You can't see what we're trying to aim for. It's just there. All right, so have a look at this. If I look at the two terms, what they share is from r equals 1 to r equals k. So one of them is missing r equals 0. So the green one is missing r equals 0, and the blue one is missing all the way up to k plus 1. So I'm just going to take those out separately. So when r equals 0, what do I get for that first one? I get k choose 0, and I get x to the k plus 1, that's right, isn't it? And a to the 0. Do you agree? Hope you agree. All right, and then now I can just take that and say, all right, I've taken the r equals 0 out, so I'm going to go from the 1 to k and keep that. K minus r plus 1, a to the r. Okay, and same here, I'm going to go this one, for the green one, I'm going to go from r equals 1 to k of our k choose r minus 1, x to the k minus r plus 1, a to the r. Oops, we're going to have to rub this out. Alright, hopefully that's all okay with you guys. Alright, but I've left out the k plus 1th kind of term in this series, so let me write that separately. So basically, look what I'm doing. I want to put those together so they both have to go from r equals 1 to k. So I've missed out the k plus 1. So what's the k plus 1? K choose k plus 1 minus 1. That would be k, wouldn't it? X. K minus, I need to write it down, minus k plus 1, plus 1, and then a to the k plus 1. Alright, so you can see that this will be k minus 1 plus 1, so that's going to be 0. So that's going to be x to the 0, and k choose k is 1, so all that's going to be left for that term, and I'll circle it, so is going to be that part there. That's all that's going to be left. And if I look at the front part as well, k choose 0 is 1, a to the 0 is 1, so all that's going to be left is that. So on the outsides I've got x to the k plus 1 and a to the k plus 1. But let's put the sum part together. So, long-winded, sorry guys. Just wanted to make sure you had bit by bit. So x to the k plus 1, that's all good. And if I now put the sum parts together, what have I got? I am definitely summing from 1 to k. And what do they have in common? They both have a to the r in common and x to the k minus r plus 1. All right, well, excellent. So what I can do is factorize. So k choose r and k choose r minus 1, but they both have x to the k minus r plus 1, and they both have a to the r. So that I'll put all that together. And then, of course, I have that last term, which is a to the k plus 1. So remember, these are just my two kind of outside terms here. All right, is it looking a bit like what we are heading towards? Hopefully. All right, so remember that if I add these two parts together here, I'm going to, so if I'm using that, that's the kth, from the kth row for the Pascal's triangle, so that'll become k plus 1. K plus 1, choose, and the bigger one of those is r. So this is what I've got. If I put those together, and I'm still summing from 1 to k, but that middle term is just using our addition. I really should rewrite this in for you and rewrite this in for you. And we would say, you know, after this line is where we would say what we've done. So we've said, basically, we've said k plus 1 choose r is made up of k choose r plus k choose r minus 1. All right, so we're welcome to use that. Now, we should have what we want now, because we really want, okay, I'll look at this before I scroll. We want to put it all together, and we want to go from 0 to k plus 1. So the moment we've got 1 to k, so clearly if I put in r equals 0 to that one, what would I get? R equals 0 would give me, it's hard to see where I'm looking, so I'm looking here. I'm going, I've got r equals 1 to k, but I really want r equals 0 to k plus 1. So I'm hoping r equals 0 gives me this term, and r equals k plus 1 gives me this term. Then I can put them back in. And so let's just check that. So if I scroll down, here we go. So let me just do some working over the side. So looking at this, if I had r equals 0, I would have k plus 1, choose 0, x to the k minus 0 plus 1, and a to the 0. Now you can see a to the 0 is 1, so that's 1. Anything choose 0, that's 1 as well. So all we have is x to the k plus 1, which is that first term. And let's try k plus 1. So if I put k plus 1 in there, for r, I will get k plus 1, choose k plus 1, x to the k minus k plus 1 plus 1, a to the k plus 1. You'll see everything goes to 1, 1, except for a to the k plus 1, which is that last term. So what I'm doing is just putting them all together from r equals 0 all the way to k plus 1. Of k plus 1, choose r, x to the k minus r plus 1, a to the r. All right, which should equal our right-hand side. So therefore we can say p of k implies p of k plus 1. Therefore p of n is true for our integral n is greater or equal to 1 by induction. So go through bit by bit and just see if you can do it yourself. Good luck.